Well, hello again, everyone. In this lecture, we're going to continue our discussion of equilibria as we've been talking about for the last several weeks. And in particular, we're going to be focusing on solubility equilibria, which has to do with sparingly soluble salts in water. And we're going to review briefly something we talked about earlier in the semester, just as a reminder, the thermodynamics of solutions. When solutions form and the equilibrium effects dominated by the thermodynamics of them. We talked about the enthalpy of solution. The enthalpy of solution, of course, as we talked about earlier, is a combination of the lattice enthalpy of whatever the compound is that's being dissolved and the enthalpy of hydration that occurs when those separated particles or ions or whatever they are dissolve in water. Now, the lattice enthalpy, as we talked about before, is always greater than zero, endothermic in other words, because it takes energy to separate all the ions or molecules or whatever the solid is composed of into individual particles. By contrast, the enthalpy of hydration is always exothermic, always less than zero, because when these separated ions dissolve in water, it's always an exothermic process, emitting energy. Now, and we're going to focus almost entirely on ionic salts dissolved in water. So we're going to be talking about ionic solutions that are aqueous. The free energy effect, of course, is a combination of both the enthalpy of solution and the entropy of solution. Now, for most solutions, the entropy is almost always greater than zero. That's because, of course, the individual particles, ions, let's say, in the salt, instead of being in a solid crystal, are being separated into individual ions in solution. So, of course, that increases the entropy of all those individual ions. I say usually greater than zero because what happens, of course, as we'll see in a minute, is that the ions in aqueous solutions, each of them are surrounded by a number of water molecules, both the cations and the anions. And these water molecules stay as essentially a coordination sphere, a clump, if you will, around the ions. And in essence, then 6 water molecules are behaving as if there were only one in terms of individual particles. So compared to all of the water molecules in the container, those that are associated with ions that are dissolved have had their entropy decrease because there are fewer of them. However, because the kinds of salts we're going to be talking about are very sparingly soluble, the number of water molecules that are like that are very, very small compared to the total number. And so the overall entropy effect is almost always positive. So because of those two effects, the enthalpy and the entropy effect, the sign of the delta G of solution is usually determined then by the sign of the delta H. If the overall delta H of solution is negative, then delta G will almost always be negative as well. And if it's positive, then delta G of solution will almost always be positive. Now, at saturation, as we talked about earlier for equilibria in general, the Gibbs energy has reached a minimum and the delta G is zero. So a way of looking at this from the standpoint of the ionic salt and its dissolution in water is kind of like this. And this is similar to one that we looked at earlier in the semester when we talked about the overall thermodynamics of solutions. If this is an ionic salt composed of some cations and some anions that are in a crystal, and they're held together by, of course, Coulombic forces. So to separate them requires energy. Well, when an ionic salt dissolves in water, water molecules, of course, essentially attack the individual crystallites by pulling the ions out of solution because of their attractive forces to each other. For example, water molecules, the oxygen partially negative side of a water molecule will essentially attach itself to a cation, and water molecules where the hydrogen side is partially positive will attach themselves to the anions. And so as this process occurs, individual ions are pulled out of solution one by one, and how fast it occurs depends on the temperature and what the solid is and so on. But the net result is that cations essentially wind up with a coordination sphere of water molecules around them, with the oxygen side of the water molecules sort of facing the cation. Similarly, for anions, it's the hydrogen side of the water molecules that face it. This is what I was talking about just a minute ago, that all 6 of these water molecules, for example, if that's the number that are coordinated, now essentially behave as if they were one. And the same thing is true for the anion. And so for that very small percentage of the water molecules, their entropy has actually decreased a bit. But overall, it's almost always an increase. So the net result of all of this is that ions are in solution by being coordinated to water molecules. Now, the net effect of these two factors, the enthalpy of the lattice and the enthalpy of hydration, we've talked about this before as well. Because the enthalpy is a state function, we can consider only the beginning point and the end point. It doesn't matter how you get from the beginning to the end. And the fact that these two processes don't occur one after the other, they occur all at the same time. Nevertheless, we can look at it that way from an energy standpoint. Here's the solid, the initial solid. To separate all those ions into individual ions, call it a gas of ions, requires this lattice energy to separate all those ions. So of course, it's always endothermic, and the energy is the delta H is positive. When these ions then dissolve in water, the process we just looked at on the last slide, the enthalpy effect is always negative. Now, the difference between these two is the enthalpy of solution. The way this diagram is drawn is intentional. The typical effect for most solids dissolving, ionic solids dissolving in water, is that the enthalpy of solution is a fairly small difference between two large numbers. And so as a result, if either of these is different by a little bit, it could cause the enthalpy of solution to have a change in sign. For example, here's one where the enthalpy of solution is negative, or exothermic, by a small amount. And here's another one where the enthalpy of solution is positive. Whereas these two values right here are typically very large numbers. In fact, in this case, it's showing the delta H of the lattice to be the same, and the differences between the two delta H's of hydration. Nevertheless, the combination, the delta H of solution, is the difference between these two effects. Now, here's an example. Again, it's one we looked at earlier in the semester. The lattice enthalpy of sodium chloride, for example, is about 787 kilojoules per mole. This is the delta H of the lattice. And the lattice enthalpy of silver chloride is about 916 kilojoules per mole. Notice that all of the values shown here are all positive because, of course, as we said, lattice enthalpies are always endothermic. This table shows examples for a few halides, fluorides, chlorides, bromides, iodides, of some cations. In particular, the two we just looked at up here, sodium chloride has a delta H of hydration of minus 784, which is not much different than the lattice enthalpy. But silver chloride has a hydration enthalpy of minus 850, which is a good bit less negative than the lattice enthalpy of silver chloride, which is 916. So the difference between the two is shown down here. The overall delta H of solution then, which is the combination of these two effects, is about plus 4 kilojoules per mole for sodium chloride, but plus 65 for silver chloride. Now, as we know, sodium chloride is still very soluble, and the reason is because the Gibbs energy is still negative because of the entropy effects, whereas silver chloride is essentially one of those very sparingly soluble materials that we've been calling insoluble, because the overall delta H of solution is very positive. And so the dissolution of silver chloride in solution is not favorable because the Gibbs energy change will almost certainly be positive. So what this has led to is the classification, the qualitative classification of ionic materials as in different categories, either soluble, slightly soluble, or insoluble. But what we're going to focus on is this insoluble column here, because as we'll see, virtually nothing is completely insoluble. It simply means very, very slightly soluble. but not zero. So, for example, nitrates and acetates and chlorates are virtually all are soluble, with a few exceptions. Perchlorates are the same. The halides are almost all mostly soluble, with a few exceptions again that are slightly or almost insoluble. And then there are the cations, sulfide, carbonate, sulfite, phosphate, hydroxide. There's a number of others that are mostly insoluble. There's a few that are soluble, usually the alkali metal versions of these anions. And so what we've been referring to qualitatively are these various categories of soluble versus insoluble. But as we'll see, almost nothing is completely insoluble. In other words, it doesn't have a solubility of zero. The quantitative terms that we use for this table are shown here in the caption below. Soluble compounds are defined as those that dissolve to the extent of 10 or more grams per liter. That's very soluble. That means you can dissolve a lot. Slightly soluble, this category here, are arbitrarily chosen to be in this range of 0.1 to 10 grams per liter. Okay? And then insoluble is simply determined to be or classified to be less than 0.1 gram per liter at room temperature. But that does not mean, as we'll see, that the solubility is actually zero. It simply is very small. And it is this equilibrium between these so-called insoluble or very, very slightly soluble materials in solution that we're going to focus on in this lecture. And what this will lead to is what we're going to simply refer to in general as solubility equilibria. Now, for ionic solids in saturated solutions, that means that you prepared a solution by taking some ionic compound, putting some of it into a container of water, stirring it or shaking it or whatever to let it equilibrate, and then measuring what's in solution. What occurs, for example, for some generalized ionic solid, AB, where there's XAs and YBs of these ions, and A has a charge of M plus, and the B has a charge of N minus. This exists as a solid. In solution then, if this equilibrates with something in solution, there will be X ions of A and Y ions of B, because that's the stoichiometry of the salt. And each of them has their appropriate charge. Now, the equilibrium that exists is between the portion of AB that was added to the water that was not dissolved at all. It's in equilibrium with ions in solution. And of course, this is reversible. It simply means that A ions and B ions are constantly being removed into solution, but ions in solution are constantly being returned to the solid. So that's what makes it an equilibrium, a dynamic equilibrium like this. So the equilibrium constant, which we'll express as concentration units, that's K sub C, is given, for this kind of equilibrium, is given its own special terminology. It's called the KSP, or equilibrium constant for solubility equilibria. And strictly speaking, as we said before, for equilibrium constants, it involves the activities, the little a's here, of the two ions. However, for very sparingly soluble materials, the concentrations of the A and B ions are so small that the concentrations are essentially exactly the same as the activities. So all we're going to focus on are concentrations, not activities. So the KSP then for this material would simply be the concentration of A to the X power times the concentration of the B ions to the Y power. So here are a couple of examples. For lead iodide, for example, in the solid form, putting it in water and letting it equilibrate with the lead ions and iodide ions in solution, this would be the equilibrium. So the KSP for lead iodide would be the concentration of lead ions times the concentration of iodide ions squared, because there's two iodides for every lead. And that KSP value is 1.4 times 10 to the minus 8. Now it's important for these kinds of equilibria to keep in mind that the lead ions and the iodide ions do not have independent concentrations. They're related by the stoichiometry of the salt. In other words, there are two iodides for every lead ion. So we always know that that's the ratio of lead ions and iodide ions in solution. And that value for the KSP of 1.4 times 10 to the minus 8 means that these two concentrations, which are always in a 1 to 2 ratio, are fixed. Now, This is the KSP value. What is the actual solubility? In other words, how many moles per liter actually dissolve? Well, we can get that from the equilibrium constant, just as we have for other equilibrium constants by using a very simplified Rice table. If we let the concentration in solution of lead be X, and the concentration of iodide is 2X, because there's two of them for every lead, squared. So the product of the two is X times 2X quantity squared, or 4X cubed, which means that I can determine the lead concentration by taking this KSP value, dividing it by 4, and then taking the cube root. And that leads to 1.5 times 10 to the minus 3 molar, 0.0015 molar. Not terribly small, but definitely a sparingly soluble salt. Now, here's another example. This is iron trihydroxide. Again, it can equilibrate with the ions in solution, which will always be in a 1:3 ratio, 3 hydroxides for every iron, right? And here's the equilibrium constant, the KSP. It's the concentration of iron 3s times the concentration of hydroxides cubed. And the value for that, which you'll find looking it up in a table of KSPs, and there's lots of them, is 1.1 times 10 to the minus 36. A very, very small number, obviously. But what is the actual solubility, the concentration of iron hydroxide in solution? Well, again, using the simple formulation that we just talked about for lead iodide, let the iron 3 concentration in solution be X, and the hydroxide is 3X quantity cubed. And so the overall KSP has to be equal to X times 3X quantity cubed, which is 27X cubed times X, or 27X to the 4th. That's what KSP is equal to, what this number has to be equal to. So to get the concentration of the iron ion, I'd have to take this number, divide it by 27, and then take the 4th root. When you do that, you find a value for the iron concentration of 4.5 times 10 to the minus 10. So in comparing, for example, the solubility of lead iodide to iron hydroxide, we can now meaningfully say that the concentration, that the solubility of lead iodide is something like 7 orders of magnitude higher than iron hydroxide. It's important to keep in mind that this concept of solubility product, the KSP, is meaningful only for sparingly soluble salts. In other words, the concept of KSP is not a valid one for very soluble materials like sodium chloride or some nitrate salt or something like that. And the reason why is because at solution concentration is higher than about 0.01 molar, 10 to the minus 2 molar, there are various effects that occur that are assumed not to occur in these kinds of calculations up here. For example, in the case of lead iodide, if, for example, the lead iodide does not completely dissociate in solution, in other words, the lead iodide does not go completely to give lead ions and 2 iodide ions. Perhaps it forms some PBI plus ions. Now, this does not actually occur for lead iodide. For lead iodide, the assumption that the KSP is valid is entirely true. We could also find that there may be some lead iodide clusters that haven't separated at all. They've simply gone into solution as PBI2 clusters. Again, this would invalidate the KSP calculation if these effects were very large. Similarly, for iron hydroxide, suppose that the FeOH3 in going into solution does not dissociate completely. Suppose there are some iron OH2 plus ions, maybe some iron OH1 2 plus ions, and so on. Again, this does not happen for iron hydroxide, but these are examples that correlate with the 2 samples I've given here. This is the reason overall, though, why at high concentrations, higher than about 10 to the minus 2 molar, the simple concept of the KSP is not entirely valid because effects like this can occur to some extent. Now, here are some values. And I'm obviously not going to go through all of these in detail. Let me lower this a bit. There are lots of numbers here, and this is only a small sampling. There are literally thousands of these for virtually every ionic compound you can imagine. But in general, you can see that the numbers given for the KSPs vary over large ranges. For example, there are some that are as small as 10 to the minus 5 or 10 to the minus 6 or 7, and some that are as small as 10 to the minus 49th or 10 to the minus 54th, and so on. This simply reflects the fact that different solids, different salts like this, have very different solubilities. Some of them are very slightly soluble, but more soluble than some others that are almost infinitesimally small in their solubilities. However, it's important to keep in mind that in comparing KSPs for different salts, the only time that two KSPs can be meaningfully compared without any calculation is if the stoichiometry of the salt is the same. In other words, I could compare copper bromide to copper chloride because they're both one-to-one salts. And in this case, I could say, yes, indeed, copper bromide is 2 orders of magnitude less soluble than copper chloride. But I can't compare, for example, something like lead chloride, right here, lead chloride to copper chloride, because the stoichiometries are different. As we just saw, the lead chloride forms 3 ions, copper chloride forms only 2, and that affects the numerical value of the KSPs, as we just looked at when we compared iron hydroxide and lead chloride in the previous figures. And in any case, in comparing KSPs, you have to be cautious about simply looking at 2 numbers and saying, well, this one is much, much less soluble than this other one. Only if they have the same stoichiometry can you say that without some calculations to show what concentrations they actually are. Here are some more from another book. Now, one of the things that happens because of this equilibrium in solution, this equilibrium of ions in solution with solids that are in equilibrium with those ions, is what's referred to as the common ion effect. Think of it this way. Suppose that we make a solution of silver chloride in water. It will equilibrate, just as we talked about before. It will equilibrate with silver ions and chloride ions in some very small concentrations. And if we started with pure water, that would be true. And we know that the silver to chloride ratio is exactly 1-to-1 because the only source of both of the 2 ions was from the silver chloride. But suppose instead of putting the silver chloride into pure water, we put it into a solution that already has some sodium chloride dissolved. Now that means that the chloride concentration is separate from the silver concentration. There was already some present, and so the ratio of these 2 is no longer 1-to-1 as it would be if we started with just pure silver chloride. And for that reason, Le Chatelier's principle tells us that less silver chloride will dissolve in a solution that already contains either some silver ions already or some chloride ions already. And that's what's referred to as the so-called common ion effect. Here's an illustration of it for, let me blow this up a bit. This is an example of it for lead sulfate. What is represented here by this curve right here is the relationship between lead ions and sulfate ions in solution. The ordinate is the molar solubility of lead sulfate in terms of moles per liter, and they're times 10 to the minus 5 as a multiplier. The abscissa corresponds to the concentration of a potassium sulfate solution. All this means is that the sulfate ions can be independently varied from the lead concentration that comes from the lead sulfate. In other words, if I dissolve lead sulfate in pure water, then the sulfate concentration is 0. So it's this point right here. And at that point, this is pure water. At that point, the lead sulfate concentration is about 13.5 times 10 to the minus 5 moles per liter. But if I measure the solubility of lead sulfate in a solution that already contains some sulfate ions that came from potassium sulfate, the concentration, the molar solubility of the lead sulfate is less. It keeps getting less and less the more sulfate was in there to begin with. And so this point that I've highlighted here with this red dot, this concentration of the initial concentration of sulfate is about 14 times 10 to the minus 4. But what it has done is it's lowered the solubility of the lead sulfate from 13.5 times 10 to the minus 5 to about 1/10 that much. It's now 1.3 times 10 to the minus 5. And so the effect of having some sulfate already present caused the solubility of the lead sulfate to be less. In this case, the sulfate ion is referred to as the common ion. It's what causes this, the application of Le Chatelier's principle to be manifested. Now, here's an illustration for silver chloride. And I realized that the way this was drawn in this book, this was a previous edition of your own book, is a little confusing. It's explained in detail in the caption down below, but if you consider just the curve itself, you'll see what this effect is that we've just been talking about. What this represents, the ordinate, is the silver ion concentration in moles per liter, and the abscissa is the chloride concentration in moles per liter. And what is demonstrated here is the same thing that we just saw for the lead sulfate in the previous figure. If we start with pure water, which is right here, it means there's no initial silver ions and no initial chloride ions to begin with. And if we add some silver chloride, the amount that will dissolve will lead to, of course, the silver ion concentration and the chloride ion concentration being exactly the same. They have to be, because they're in a 1-to-1 ratio. And so what this red arrow is showing is the progression of the dissolution until it reaches this equilibrium line curve here, all right? And the amount of each that dissolved is the same. The concentration of silver ions in solution is 1.3 times 10 to the minus 5, which is the length of this green line. It's qualitatively representing it that way. And the concentration of chloride ions has to be the same, 1.3 times 10 to the minus 5, and that's this line right here. And so at this point right here, this would represent the concentrations of silver and chloride ions, which are equal to each other, in being dissolved in pure water. However, if instead of pure water, we start with a solution that already contains 4 times 10 to the minus 5 molar of silver nitrates. In other words, what that's done is it has some silver ions already in solution at a concentration of 4 times 10 to the minus 5. So that's this point right here. What it would mean is that the maximum amount of silver chloride that could dissolve is less because there's already some silver ions in solution. And so now the length of this little green line represents how much silver chloride would dissolve in that solution that already contains 4 times 10 to the minus 5 molar of silver ions from the silver nitrate. The same thing is true if I start with a solution that already contains 4 times 10 to the minus 5 molar sodium chloride. Now there's some chloride present already. And so as a result, the amount of silver chloride that could dissolve, represented by this little green line here, is less. It is considerably less than the 1.3 times 10 to the minus 5 that would have happened if it were pure water. And that is another illustration of this so-called common ion effect. Now, one of the things that all of this leads to is the effect or the interaction of ions in solution when precipitation occurs. You're all familiar with precipitation when something is added to something else and you see a solid come out of solution as a precipitate. It's all governed by this solubility equilibrium. Now, if we look at the curve that occurs, this was that one we just looked at for silver chloride, representing it slightly differently. This is the silver ion concentration right here. This is the chloride concentration. And if we look at it from an equilibrium standpoint, this line right here represents the solubility equilibrium, the KSP of silver chloride. In other words, the product of the two concentrations, the silver concentration times the chloride concentration, has to equal the KSP, just like any other equilibrium constant, 1.8 times 10 to the minus 10 in this case. Right? Now, if you remember what we talked about earlier when we were discussing the effect of different conditions on the equilibrium constant for a reaction, and we said that if we start with a condition where Q is larger than an equilibrium constant, then the system will adjust itself to approach the equilibrium line, where Q here is equal to the KSP in this case. And so anywhere in this region out here, anywhere out there, the combination of the silver concentration from whatever source and the chloride concentration from whatever source is larger than the KSP, the product of the two. All right. And so what will happen because of that is the system will adjust itself to approach the equilibrium line, where now Q has become equal to the KSP. And so the system will stay there unless you make some more adjustments. All right. Similarly, if the combination of the silver concentration and the chloride were anywhere in this region, down below the equilibrium line, now the Q is less than the KSP, which means that more of the silver chloride could dissolve until, again, it reaches the equilibrium line. So now the Q has become equal to KSP, and that's where the system will stay, all right, Q equal to KSP, unless it's adjusted again. And so that's an important effect that occurs when precipitation occurs. When precipitation occurs like this, it simply means that the concentrations of the two ions that constitute a potential precipitate, concentrations of the two ions are such that their combination in a KSP expression is larger than the KSP is. Q is larger than KSP. And so in that case, no matter where these two ions came from, silver chloride will precipitate until the concentrations are somewhere on this line. Okay. Now, one of the things that this leads to is the possibility of what's called selective precipitation. This is a little bit more complicated, and I'm not going to go through all the details of it, but you'll get the idea as we proceed through this. This is another example of the concentrations of metal ions and chloride ions. In this case, there are two metal ions, silver plus ions and lead 2 plus ions. Okay, and the abscissa are the chloride ion concentrations. And so anywhere in this white region down here, the concentrations of the silver, the lead, and the chloride are such that it is not at equilibrium, and so no precipitation of either one of those two salts will occur. What will happen instead is that more of them could dissolve until this line is reached right here. This is the line where the Q now is equal to the KSP of silver chloride. And the reason that is shown this way is that the KSP of silver chloride is about 5 orders of magnitude less than the KSP of lead chloride. And so as long as the solution contains ion concentrations that make it lie somewhere in this white region, neither of the two will precipitate. And what they're representing here is that no silver chloride is a solid and no lead chloride as a solid. So similarly, in this blue region up here, now the combination of the three ions, the silver, the lead, and the chloride, are such that both silver chloride and lead chloride precipitate because the Q is larger than the KSP of either one of those two salts. And so what will happen is that both of them will precipitate until this line is reached. Now, the point of this figure is what's in between, this yellow region here. This line right here, as we just said, represents the line for which the Q is equal to the KSP of silver chloride. This line represents the point at which the Q is equal to the KSP of lead chloride, which means it's also, of course, larger than the KSP of silver chloride. Now, what occurs here, suppose that we start with a solution that contains all three ions, the silver, the lead, and the chloride, with some arbitrary combination of the ions. And let's suppose that it's somewhere in this region. What will happen is that silver chloride will precipitate because this region represents a region where the Q is larger than the KSP of silver chloride. It doesn't show that here. Anywhere in this region, the Q is larger than the KSP of silver chloride. And so what will happen is that the silver chloride will precipitate until it reaches this line. But lead chloride in this region will not precipitate because in this region, the Q is less than the KSP of lead chloride. You'd have to be beyond this line, somewhere in here, for the lead chloride to precipitate. So the upshot of all of this is that if I have a solution of chlorides that contain lead and silver ions, I can separate the two by adding either some more chloride that will cause, if I'm somewhere in this region, that will cause the silver chloride to precipitate but leave the lead chloride in solution. And because the KSPs differ by several orders of magnitude, I essentially have what amounts to practically 0 silver ions left in solution, but the lead chloride is still in solution. And that's what this so-called selective precipitation occurs to happen. And it's all because of this effect right here, the so-called common ion effect. So